This room is a decent temperature. I like it. It's not cold.
Yeah.
I'm very happy.
It's very warm for me.
Yeah, it's a lot hot.
I guess it's my European part. That's just very happy. It's not 65 Fahrenheit in here. Take that now.
And see you.
I know.
So, I'm sorry.
How dare you.
Sorry, Stefan. But what are you doing tonight, by the way, Stefan? Do you want to come to personal best at 8 for girls' night?
Yes, I'm so down. I have a perfect happy hour once it's about there.
And what time is your happy hour?
What? A CTG.
Okay, 4:30. Okay, that's a bit of a very bad timing. But
That's okay. I'll see you later, Nick.
yeah, you know, I wasn't normal talking. Like, yeah,
You can come. You can come. You can come to personal best.
you can come to girls' night. I mean, 4:30 is more like a snack with alcohol. I would think.
So nice that we have a professional photographer in the lab.
That's true. You guys have lucky. Actually, my mom obsessed with that. Very good.
Everything's looking good. I think we might actually run tomorrow. So I got the parts from the shop and I haven't done like a full integration test, but like, you know, the thing that I was actually worried about, which is if they're going to couple to the handles, actually works. So hypothetically, we're good to go.
Okay.
See.
It's a meal online.
Yeah, I have your assistance. Oh, shoot, you're not
Exactly. Yeah, I know. Yeah.
Grab that, dude.
I was like, I just, as much as I think it's gonna be, you know, safe and robust, I'm also like, I think it'd be really sketchy for someone to have a motorized system that, yeah,
No, yeah.
it's definitely not ready to just give to everyone and be like, yeah, you know.
You mean you don't have my angular resolved data set already?
What I really mean is, I don't want someone to turn the motors too much and break something. The safeties are built in. Hypothetically, it won't, but you know.
You never know.
Oh, there's always a way.
Yeah, there's always.
And then Dimitri's here.
To the place where you asked Nick a question to be relayed to me and Evan this morning regarding the low energy water attachment cross sections. You should have to clarify, not later, what exactly you were referring to.
Yeah.
Okay.
After this or at happy hour.
Okay. Yeah, that sounds good. Yeah. Check.
It was to get his seat, right?
I can check.
I
That
was,
was you in his master's degree, was it officially?
I was, even like, I'm in trouble standing right now because this is, I know exactly what the question is being asked. The answer has been.
I have other ways of getting information,
Sure,
but
you want.
I thought that was. You know, that you
That is
found
true.
that in it, but that logic like wasn't connected in my brain.
I think theoretically the PDF is supposed to link to it as well, but it doesn't.
Yeah, I don't think it does, because it
The
just like
system's
has,
a little broken. Yeah.
yeah.
It's also like a million degrees from here.
It always is.
Yeah.
It's stuck.
I was the only one very happy about that.
I think it's more than typically is. I mean, that also, yeah, that's funny.
It's also like 65. The whole
And you don't.
He's our office is not very full. It's too crowded. Maybe I went into it's hosting in our office.
Can you hear us?
Oh, yeah, you did.
Yeah, I can hear you.
Awesome. Can you hear us back here? Danielle?
Yes, yeah, I can hear you too.
That works. And the podium? Oh, here, you can sit there. It's just stands over here.
I'm pretty sure those thermostats are set to remote control.
Figure out to see what colors
You're supposed to be able to change that band. I like the music.
Right. If everyone's ready, it would be okay. Let's start by introducing. Okay. Neil, that's okay. Okay with you? Start introductions? Okay, great. Okay, so I'd like to, as the chair of the committee and Rafid's advisor, give a brief introduction of his path here today. So Rafid came to Cornell in 2020. The 2020 matriculating class came in with a master's degree in fluid mechanics from École Polytechnique, which is one of the most prestigious technical universities in France. And he actually delayed matriculation by one semester and started formally in 2021 because of the COVID-19 pandemic. Just to give context, where we all started back then. Rafid's first major project in our group called Astrolab, which even changed the meaning of its acronym since that time. Our group was more of sort of a concept at that time than what it is today. So that first project was molecular dynamics modeling of the collisions of the ion plumes that come from the spacecraft propulsion devices that we work on with surfaces. And Rafid represented our newly formed lab in this work on a project that was sponsored by NASA. And there's really a lot of high visibility in the community. And with this initial project and the work that followed from it, Rafid developed new simulation capabilities that have really propelled an entirely new arm of research in our group that I didn't know, that we were going to pursue from the beginning, and that was to be so successful and so informative for our field. And it's really transformed the way that our community understands some really important physical processes in our engineering system. And thanks to Rafid's work, people kind of think of our group as experts in molecular dynamics in the field, which is something that I never did. So glad that you passed that knowledge on to other people in the lab to carry on. So I thought I'd include here a quote from my letter of recommendation that I recently wrote for Rafid. So Rafid has been a dream student to work with and has been absolutely integral to building my lab's research program. So I'm very grateful to Rafid, as previously the summer to Carl, for taking the chance to become a PhD student, the second one in this newly formed group, helping me build this research program and trailblazing the numerical arm. So it's really neat for this semester to have sort of those, first defenses in these two fields that we really successfully developed with your hard work. So I'd say, one last thing to say is Rafid is excellent at technical communication. You'll see that today. And I can't take credit for that because you've had that skill since day one. And Rafid hopes to become a faculty member in the future, build his own lab, maybe even delving into some experimental work. We'll see. No doubt he will excel in that role, whatever path he takes. So Rafid has taught me a lot over the past 5 years working together, and we'll all learn something today. So
Thank you so much. I'm ready to start.
Yeah.
Okay. So hello everyone. Thank you for coming. Today I'm going to present the research that I did for my PhD that I titled Advancing Space Electric Propulsion through Optimization of On-Orbit Refueling for Planet Discovery and Molecular Modeling of Electrosphere cluster plumes. And as per the title, this research addresses different topics related to space electric propulsion. So I will start by giving a quick motivation for why we need space, why we need propulsion in space. So we need propulsion mainly for orbital maneuvers, whether for impulsive maneuvers with chemical propulsion, as shown in A, or for continuous thrust maneuvers with electric propulsion, as shown in B. We may also need propulsion for attitude control if a spacecraft is subject to external perturbations. So we need to apply force to counter these perturbations to get a stabilized system, as shown in C. And these maneuvers, the cost of these maneuvers is measured by the amount of the velocity change delta V. And this table shows some examples for two different missions. It gives the cost of orbit insertion and station keeping per year in meters per second. And there are two primary ways to produce thrust. The first one is chemical propulsion. In this case, the energy is stored in the bonds of the molecules, and then through a chemical reaction, the bonds break, and the chemical energy is released and converted into kinetic energy for the spacecraft. Second way is electric propulsion. This one relies on an external source of energy, generally the sun. So we have to collect the source of energy first, and then through a conversion mechanism, and through the application of a difference of potential, we can extract ions at very high speed, and then we can convert this energy into kinetic energy for the spacecraft. And chemical propulsion is characterized by high thrust and low mass efficiency, while electric propulsion is characterized by low thrust and high mass efficiency. And the mass efficiency is measured by a metric called specific impulse that is defined as the ratio of the exhaust velocity, C, over the standard gravity, G. And for example, if you have two spacecraft, one that uses chemical propulsion in red and one that uses electric propulsion in blue, the one that uses electric propulsion would have a higher I speed, and therefore it will be able to achieve a higher velocity change than V. And this figure here shows the specific impulse in second as a function of the thrust in micronewton, and it shows different propulsion systems. And the electric systems are shown in this bluish color, and they are all located in the top left region that represents the region of high specific impulse and low thrust. And the delta V of the mission and the I speed are related to each other with the rocket equation that gives the propellant mass as a function of the total mass of the spacecraft and as a function of the delta V of the mission and specific impulse of the thruster. But since the delta V is fixed by the orbital requirements of the mission, if we want to decrease the propellant mass, we need to select the thruster with a higher specific impulse I speed. And this figure on the right shows the propellant mass fraction as a function of the delta V of the mission for chemical propulsion and electric propulsion. So we took nominal values of ISP between 200 and 500 for chemical propulsion and 1,000 and 5,000 for electric propulsion. And the figure shows that for all delta V, the electric propulsion always requires less propellant, and chemical and electric propulsion lie in two different regions. And in this thesis, we're going to focus on the electric propulsion part, so in the bottom region here. And this thesis is composed of three main parts. The first part is at the mission level. In this part, we're going to develop an analytic framework to quantify the benefits of refueling for spacecraft using electric propulsion. Then in part 2 and 3, we're going to focus on one single type of thrusters called electrosphere thrusters. So part 2 is at the propellant level. We will develop a computational framework to identify new aerotic liquids that could be used as propellants for electrosphere thrusters. And in part 3, we're going to also develop a computational framework to investigate the molecular processes in the plumes of electrosphere thrusters. So let's start with part 1 at the mission level. The current space industry architecture is based on single-use systems where each spacecraft is designed as a disposable unit. And this causes high launch mass and cost because the spacecraft must carry all the fuel from the ground during the launch. And in this architecture, the fuel represents the main limiting factor, and it leads to a limited flexibility of the operations during the mission. The alternative space industry architecture is based on refueling, and the ability to refuel a spacecraft during the mission allows for lower launch mass and costs. It also allows for adaptable operations during the mission, and it leads to high sustainability and reusability of spacecraft. And previous studies in the literature have addressed on-orbit refueling from operational and technological perspectives, and most papers have focused on simulations for case-specific missions. So however, there is a gap in the fundamental understanding of how refueling affects the mission, and a generalized framework to quantify the intrinsic benefits of refueling is missing. And this gap exists in both chemical and electric propulsion. However, in this work, we are going to focus on electric propulsion only, but we can easily generalize the results here to include chemical propulsion in the future. And the goal of this work here is to define performance metrics for refueling, starting from first principle equations of electric propulsion. So I will start by giving a quick introduction to the Stallinger theory for electric propulsion without refueling. Stallinger was a German-American scientist who wrote many papers about electric propulsion. And namely, he wrote this paper from 1967, where he introduced an important quantity called the normalized payload and structure mass. It is defined as the mass of the payload plus the mass of the structure, normalized by the total mass of the spacecraft. And then he derived an expression for this metric using these underlying equations So he used the mass budget, that is the total mass of the spacecraft, that is equal to the mass of the power system, MPS, plus the mass of the power, plus the mass of the structure, plus the mass of the payload. And then he used the rocket equation, and he used an expression for the mass of the power system that gives the mass of the power system as proportional to the power. And then he assumed a constant mass flow rate. And then he derived this equation. So that gives h as a function of the delta v of the mission and the exhaust velocity c of the thruster, and as a function of the characteristic velocity dch. And this characteristic velocity is also called the Stallinger velocity, and it represents the theoretical upper limit velocity that an electric thruster can achieve. And it is a function of eta, the power efficiency, alpha, the specific mass of the power system, and the firing time here. And then he normalized these quantities with respect to the characteristic velocity. So we have this normalized delta V and normalized specific impulse that are normalized with respect to the power to VCH. And then we can write h as a function of these normalized quantities. And the figure on the right shows the metric h as a function of the normalized specific impulse C bar for different values of delta V bar between 0.1 and 0.8. And we can observe that for a value of delta V bar equal to 0.8, the normalized payload mass is negative, which means that the mission is not feasible. So the main result from this Stallinger theory is that the maximum delta V for which a positive payload mass can be carried is 0.8 delta V, 0.8 VCH. Now I will follow the same approach as Stallinger and apply it to a mission with refueling. So let's consider a mission that starts from an orbit R0 and goes to a final orbit Rn. And along the mission, we have n-1 refueling stations. So we can subdivide the mission into n segments. And the total requirement for the mission is delta V. So at each segment, we have to achieve a fraction of this total delta V, that is beta I times delta V, with beta I between 0 and 1. So the sum of all the fractions of beta I delta V has to be equal to the total delta V. And therefore, the sum of the coefficients has to be equal to 1. And for the specific case of a mission without refueling, we have n, the number of segments, equal to 1 and beta equal to 1. And then we follow the same approach. So we apply a piecewise mass budget, which is similar to the one that we showed earlier. But here we have this subscript I that represents the segment I of the mission. And we can apply a piecewise rocket equation that gives us MPI, which is the mass of the propellant needed to complete the segment I of the mission. And then we can get the total mass of the propellant needed to complete all the segments. And we note that the sum of all MPI is greater or equal to the mass of the propellant if we had only one segment. And so this is the first result of this these equations. So the total propellant mass over all mission segments is larger than that of mission without refueling. And we can visualize this result in the figure on the right that gives the total mass of the spacecraft as a function of time normalized to 1. And the case of no refueling is shown in orange. So we see a decrease in the mass of the spacecraft as we consume more fuel. And the average transported mass is shown in this diamond marker. And the case of refueling is shown in purple. And it shows that when we have refueling, we can consume some part of the fuel and then we can refuel. So we have these cycles of mass increase and decrease. And the average mass is also shown in this diamond marker. And we can observe that the average mass transported when we have refueling is higher than the average mass when we don't have refueling, which explains why we need more energy in total. So we need more propellant in total for the mission. And if we project the results of A into B, we can see that the sum of the segments is larger than having one single segment. Then we can derive a piecewise normalized payload and structure mass, HI. So theoretically, at each segment, we can deliver some payload mass. However, in practice, the same payload mass has to be carried from the beginning to the end. So the actual payload mass of the entire mission is equal to the minimum HI. And minimum HI corresponds to maximum beta I, which is the longest segment of the mission, which means that the actual payload mass of the mission is constrained by the longest segment of the mission because it has the highest requirement.
Sorry, Rafid, you're saying the longest segment, but you mean the largest delta V?
Yes, yes, yeah. So in space of delta V, it's the longest. Yeah. And yeah, so we can take this expression and we can optimize it analytically. And you can show that the vector that maximizes H star is a uniform vector of values 1 over n, which means that the payload mass is maximized when the distribution of beta I is uniform. So having uniform distribution of refueling stations maximizes the payload mass. And we can also show that the derivative with respect to n is positive, which means that the payload mass increases as the number of refueling stations increases as well. Then you can show the values of H star as a function of the normalized specific impulse, C bar, for different values of n. N is the number of mission segments. And we do it for the extreme case where delta V is equal to 0.8 times the characteristic velocity. So the case of no refueling corresponds to n equals 1. And as we have seen earlier, the payload mass is negative, so the mission is not feasible. However, if we introduce refueling, then the payload mass becomes positive and the mission becomes feasible. So this means that refueling can enable some missions that are otherwise not feasible. And then you can plot the optimal specific impulse that maximizes H star. And we can ignore the first value in the second plot because it corresponds to a negative payload mass, so it is not realistic. And then starting from the second value, we see a decrease in the optimal C bar. So this shows that the optimal specific impulse decreases as more refueling is available. We can also show that there is an upper limit for H star by taking the limit of n to infinity. So H converges to this quantity here. And you can also visualize it here in this figure for given values of delta V and specific impulse. So this shows the mass fraction as a function of the number of mission segments. And we have a constant fraction that is dedicated to the power system. And then when we have more refueling, the requirement on the propellant mass decreases. So we can see a decrease in MPI in purple. And this gain in mass can be used as a payload. So we see an increase in the normalized payload mass in orange. And however, after some value, we reach some plateau. So more refueling stations is not beneficial after a certain threshold when we are very close to H infinity. And then we can also define some performance metrics based on time considerations. And for low thrust maneuvers, the mission time can be approximated by the firing time because we have continuous thrust. And if we assume a constant mass flow rate, we can show that the firing time ratio that is defined as the firing time with refueling over the firing time without refueling, we can show that this quantity is greater or equal to 1 as well. So missions with refueling are intrinsically longer than missions without refueling. And we can also show using Lagrange multipliers that this quantity, this ratio tau, is minimized if we don't have any refueling, if beta is just one single value, and it is maximized if we have a uniformly distributed refueling. However, in this case, we want to minimize tau, so we end up in two extreme cases. In case A, we want to maximize the payload mass, so we want to have an evenly distributed refueling. In case B, we want to minimize the mission time. In this case, we want to avoid refueling. So in practice, we may want to maximize the payload mass while having some constraints on time. So the actual optimal would lay somewhere between the two extreme cases. And then we are going to apply this framework for an actual mission. And we choose the SMART 1 mission. SMART 1 was an ESA mission from in 2003. And after insertion into GTO orbit, it uses Hall effect thrusters to achieve lunar orbit. And from the literature, we can get these reported values of the mass budget, as well as the power, the ISP, the thrust, etc. And we can use them to calculate other metrics that we need for our upcoming analysis. And then we can define an optimization and a constraints problem. That is for given values of normalized delta V and normalized specific impulse, find the refueling sequence of beta I that maximizes the normalized payload mass under these constraints. So the coefficients beta I have to be between 0 and 1, and the sum of beta I has to be equal to 1. And n, the number of segments, has to be smaller than some n max that we can prescribe. And tau, the firing time ratio that has to be smaller than some tau max that we can prescribe as well. Then we use a numerical method to solve this optimization problem. And we use a local optimizer followed by a global optimizer because the local optimizer can find the local minimum. And if we naively use only a local optimizer, it is going to be stuck in one single minimum. So we need a global optimizer to explore all the space. And then we apply this optimization for 4 different cases. In all cases, we fix n max to 10, which is the maximum number of segments. And then we vary the constraint on time. Initially, tau max is 1, which means that we don't want longer missions. We want the time of the mission to be exactly the same as the SMART 1 mission. And then we can relax the constraint on time until case 4, where we don't have any constraint on time. And here are the results. So if we don't want longer missions in terms of time, we have to avoid refueling and go from point A to point B without any refueling. And then as the constraint on time relaxes, we can allow for more refueling until we don't have any constraint in case 4. In this case, we can have as many refueling as possible. This case and max is 10. And here are the values of the different metrics. We can focus on case 1 and 4 for comparison. So initially we had 0.51, which is 51% for the normalized payload and structure mass, and it goes up to 71% when we have refueling. So we have an increase of 20% in terms of the payload and structure mass. And tau goes from 1 to 1.10, which means that this increase in the payload mass comes at the cost of a 10% longer mission. We also observe that H10 is about 97% H infinity. So having more refueling than 10 here is not beneficial. And now we are going to talk about some design implications for when we have refueling. So as the number of refueling stations increases, the optimal specific impulse decreases. So we may want to choose a thruster with a lower ISP. For example, we may prefer a whole effect thruster instead of a gridded ion thruster. Also, when the specific impulse decreases, the power requirements decrease, so we may downsize the solar arrays. We can also use smaller tanks. And also, since the payload mass increases, the structure must accommodate the additional payload mass and volume. There's also some logistics considerations. So in the literature, there's different ways to achieve refueling. So the spacecraft can go to the refueling hub and take fuel, or the hub can go to the spacecraft and give it fuel. And in the third scenario, we can have a distributor, a third spacecraft, that would go to the refueling hub to take fuel and deliver it to the operational spacecraft. And we have assumed in this study that refueling is consistently available at any point in the mission, and that the refueling does not alter the spacecraft's velocity vector, and that there is no additional delta V penalty or time penalty. So in this case, the scenario that agrees with our assumptions is the third scenario, where we have a distributor that would assume all responsibility for the resource transportation maneuvers. Additionally, if we want to do the refueling during orbit raising, we may take advantage of the fact that the spacecraft is following a spiral orbit, so we can put the distributor in a location that intersects with these spirals to avoid any unnecessary maneuvers. Then we can also talk about some economic considerations, and the cost of building an infrastructure can be amortized across multiple missions. And we can do this break-even analysis. We put the cost of refueling on one side and the cost of no refueling on the other side. So when we have refueling, there's this constant cost of building the infrastructure, the infra, plus n times the cost of each mission. And on the other side, when we don't have refueling, we only have n times the cost of missions without refueling. And we can derive this expression for n break-even. That is the minimum number of missions that we need in order to amortize the building of the infrastructure. And just for example, to visualize these results, so we can take the cost of the infrastructure equal to 20 times the cost of a regular mission, and the cost of a mission with refueling equal to 2/3 the cost of mission without refueling, which means that at each mission we save 1/3 of the cost if we do refueling. And you can show here the total cost as a function of the number of space missions. The red line represents the cost with no refueling, so it starts at 0 and it decreases. And the cost of refueling is in green, so it starts at the cost of the infrastructure at the beginning, and then it increases as well. And then we have this intersection in n break-even, and in the left region we are in the loss region, and on the right we are in the profit region. So based on these numbers that I arbitrarily chose, we need at least 60 missions in order to amortize the cost of the infrastructure. So here are the main results of this work. So we have shown that in-space refueling enables missions with higher delta V and higher payload mass, and that the optimal specific impulse decreases as more refueling is available, and that the payload mass is maximized when refueling is evenly distributed, and that there is a theoretical upper limit of the potential benefit of refueling, and that the gain of the payload mass comes at the cost of a slightly longer mission time. And we have to keep in mind that this analysis assumes no time penalty and no delta V penalty. And this work is going to be published in the Journal of Spacecraft and Rockets. And for the future, we can expand the system boundaries to include the distributor and the refueling hub in the optimization. We can also go from mission level to portfolio level optimization to optimize for several missions that share the same resources. And we can also do some trajectory planning to by embedding this optimization framework into a simulation environment such as GMAT. And this is just a diagram of the proposed portfolio level optimization. So we can have optimizations at 2 layers. So initially we can have single mission optimizations, and then we can take into consideration the infrastructural variables, such as the number of distributors and number of hubs, and the location of these distributors and hubs. And then we can try to minimize the cost of the refueling maneuvers. So this is the end of part 1. Now we're going to part 2, propellant level. And from now on, we're going to focus on one single type of thrusters called HO-sphere thrusters. So we'll start by giving a quick introduction to HO-sphere thrusters. So HO-sphere thrusters are a type of electric propulsion systems that are used for micropropulsion. And these thrusters are very scalable. For example, we have a spacecraft here that has a propulsion unit, and the propulsion unit has many arrays, and each array has hundreds of electrons per array emitters. And each electrons per emitter is at the scale of hundreds of micrometers, as shown in the figure. And here are some reported values of thrust and ISP for 2 different thrusters that use 2 different propellants. Now we are going to focus on one single emitter that is shown on this diagram here. So HO-sphere thrusters use ionic liquids as propellants, and they apply a strong electric field to extract ions from these ionic liquids. And ionic liquids are molten salts composed of a pair of a cation and an anion, and they are liquids at room temperature and at very low pressure, so there's no need for pressurization or heating or ionization. And the performance metrics of HO-sphere thrusters depend on the physical properties of the ionic liquids that are used as propellant. And there is thousands of cations and thousands of anions, so potentially we can synthesize millions of ionic liquids. However, a comprehensive experimental characterization is not feasible, so we need a computational model to screen all these ionic liquids and exploit the experimental available data to evaluate the unknown ionic liquids, which is the goal of this work. And it has been shown from electrohydrodynamics simulations and experiments that for an ionic liquid to be considered as a good propellant, it has to satisfy some physical requirements in terms of surface tension, viscosity, density, electrical conductivity, electrochemical window, and solvation energy. However, due to the unavailability of data, in this study, we're only going to focus on the 3 first properties. So if an ionic liquid satisfies the 3 first properties, it will be considered as a good propellant for HO-sphere thrusters. And here's the general approach of this work. So we start with a data set of ionic liquids with their values of density, viscosity, and surface tension. Then we apply filters based on our requirements. And if an ionic liquid satisfies all these requirements, it will be labeled as suitable, +1. Otherwise, it will be labeled as unsuitable for HO-sphere thrusters, which is -1. Then through a learning process using machine learning, we are going to learn some patterns in the molecular structure of these ionic liquids in order to build a classifier. And the classifier should be capable of predicting the suitability of these ionic liquids without any prior knowledge of their physical properties. Then we are going to apply this classifier to ionic liquids with unknown properties. And we need to represent these molecules in a format that is readable by the machine. In this case, we use the SMILES representation. SMILES stands for Simplified Molecular Input Line Entry System. And it is a notation that allows to represent the molecules in a string of characters. And in the table on the left, we can see some symbols of the SMILES representation and their meaning. For example, a dash sign represents a single bond, and an equal sign represents a double bond, etc. And on the right, we have some examples. We have 2 molecules, EMI plus and BF4-, and we have their corresponding SMILES representation. Then, from the SMILES representation, we use the updated library to represent the molecules in a molecular graph, where the atoms are represented by the nodes of the graph and the bonds are represented by the edges of the graph. Then we use a second library, the Modred library, to calculate the molecular descriptors of these molecules. And Modred can calculate more than 1,800 descriptors, and these descriptors can describe the constitutional, topological, geometric, and electronic properties of these molecules, and they are used for drug discovery and material science generally. And we have more than 1,800 descriptors. So here we just give some examples. For example, we have the descriptor that describes the graph theoretical radius. That is the number of nodes between the central node and the farthest node. There is the geometric radius, which is just the 3D radius for the molecule. There is the molecular weight, the number of aromatic rings, etc. So we start with a smart representation in a string of characters. Then we go to molecular graphs. Then we go to molecular descriptors. So in the first step, we represent the molecule in arrays of actual numbers that can be used for training the machine learning algorithms. And we use 3 databases, one for density, one for viscosity, and one for surface tension, that are shown here. So we see the distribution of density, viscosity, and surface tension in the data set. And the dashed red line represents the requirements that we need to satisfy. And as we see, we have a lot of missing data, mainly for surface tension. So we have only liquids that are only described by 1 or 2 properties. And then among these 2,261 only liquids, actually most of them are rejected. So we have 1,782 that are rejected because they don't satisfy at least one requirement. And we only have 14 accepted examples because they satisfy all the requirements. And the rest are uncertain because we have missing data. So they do satisfy 1 or 2 requirements, but we have missing data about the rest, so we cannot tell if they are accepted or rejected. And we represent them in this figure here that gives the anion mass as a function of the cation mass. The rejected ones are represented in red, the uncertain ones in blue, and the accepted ones in green. And as you can see, the data is extremely imbalanced. We have less than 1% of positive examples. And if we keep the data as it is, the classifier is going to be biased towards the majority class. So we need to treat this imbalanced data. And it is recommended in the literature to use oversampling of the minority class followed by undersampling of the majority class. And for oversampling, we use this algorithm called SMOTE, synthetic minority oversampling technique. For example, if we have a majority class of blue circles and a minority class of red squares, we can use the nearest neighbors of these red squares to build some synthetic data in order to balance the data set. And we have different hyperparameters that we can tune. So we can select the percentage of oversampling and undersampling. We can also select the number of nearest neighbors. And we can choose the best combination after doing some grid search. And then we explore 4 different algorithms: logistic regression, support vector machine, random forest, and XGBoost. Logistic regression tries to estimate the probability that a given instance belongs to the positive class using a logistic function. And if the probability is higher than some threshold, it predicts +1, otherwise it predicts -1. And we also do regularization to avoid overfitting. And we have many hyperparameters that we can tune. And second algorithm is the support vector machine, SVM. The SVM tries to maximize the margin. The margin is the minimum distance between the separating hyperplane and the closest point. This is shown in gamma in this figure. So the SVM tries to maximize the gamma. And we also use kernels with the SVM. Kernels allow to represent the data in a higher dimension. So if the data is not linearly separable in a small dimension, small d, we can represent it in a higher dimension, big D, that is much larger than small d. And in this larger dimension, the data is linearly separable. We also have different hyperparameters that we can tune. And the third algorithm is random forest. Random forest is built by many decision trees. It's an ensemble learning method. And each tree is built from a randomly selected subset of training sets and features. And each tree gives a prediction. Then we get the final prediction by majority group. And we can also select the number of trees, the maximum tree depth, etc. The fourth algorithm is XGBoost. XGBoost builds a sequence of decision trees as weak learners, and each weak learner makes mistakes. Then we increase the weight of the mistakes, so the second weak learner can learn from the mistakes of the previous one, until the final classifier will learn from all the mistakes of the previous learners. We can also choose the number of trees and the learning rate, etc. Then we need some performance metrics to evaluate and assess how well the algorithm performs. So we have precision that is defined as true positives over true positives plus false positives. It represents the accuracy of positive predictions. There is recall that is defined as true positives over true positives plus false negatives. And it represents the ability to identify all the positive instances. And there is the F1 score that is the balance between the two. It is defined as the harmonic mean of precision and recall. And for our work, we choose the F1 score as our objective function. So we want to maximize this value. And we also use two other metrics just for comparison. One is the Matthews correlation coefficient, MCC. This one contains all the 4 terms, true positives and negatives, and false positives and negatives. So it is a holistic metric. And we also use the area under the precision recall curve that quantifies the trade-off between precision and recall as well. So this is the general workflow. So after applying the filters and giving the actual label, we calculate the molecular descriptors from the smart representation. Then we do oversampling, undersampling, and scaling. Then we do a 5-fold cross-validation to select the hyperparameters. Then we give our predictions. Then we compare the predicted labels with the actual labels, and we calculate the precision recall, F1 score, etc. And here are the results for the 4 algorithms for training and testing. And after examining all these results, we find that the SVM is the best performing algorithm. However, these values are based on one single test set that is extremely imbalanced. So in the test set, we only have 3 positive examples and 250 so we only have 3 positives and 250 negatives. So it is extremely imbalanced. So in order to get more statistically reliable results, we do bootstrap sampling. So from the original test set, we can create n bootstrap samples by repeatedly sampling with replacement from the original data set. And then we can apply and evaluate our algorithm in these n samples. And after 10,000 evaluations, we have these results. So we have the F1 score, precision, recall, MCC, and area under the curve. The red dot represents the mean, and the blue line represents the 95% confidence interval. And if we look at the F1 score, the mean is 0.62, which is good considering the fact that we only had 3 positives for 350 negatives. And now that we have the best performing algorithm and we know how well it performs, we can apply it to our unknown ionic liquids. So as we have mentioned before, we had 465 uncertain examples shown in blue. And then we apply our classifier. And among these 465, we can find 19 positive examples that are shown in black crosses here. And these are some examples of the newly discovered candidates. So we have pairs of a cation and an anion. And so we have 19 of them. However, we are not satisfied with only 19 candidates, so we want to have more candidates. So we construct a new data set. So we take a list of more than 900 cations and more than 200 anions, and we combine them, and we get about 250,000 ionic-like molecules. And we call them ionic-like molecules because there is no guarantee that all the combinations give actual ionic liquids. And then we calculate the molecular descriptors for these molecules, and we apply the SVM. And among these 250,000 ionic-like molecules, we find 193 positive examples. So we represent them in this next figure. It shows the anion mass as a function of the cation mass. And among these 193 examples, we have 14 from direct filtering that were used for training. We have and they are shown in green circles. We have 19 from the actual data set. They are shown in black crosses. And we have 160 from the constructed data set. They are shown in blue diamonds. And if we look to the left figure here, we see that we see the bounds of the data set, and all the positive examples are located in this restricted region. This is because the positive examples used for training were also restricted in this region. So the classifier was able to interpolate, however, it is unable to extrapolate. So we may have some actual positives in this empty region, but the classifier was not able to calculate them. And for conclusion, these are the achievements for this work. We have calculated the molecular descriptors of ionic liquids from the smart representation, and we have manually labeled them based on density, viscosity, and surface tension requirements. And we have applied resampling techniques to address imbalanced data. And we have tested 4 different algorithms and found that the SVM was the best performing algorithm. And then we have identified 193 potential propellants for electrospray clusters. And this work was published in the Journal of Electric Propulsion this year. And for the future, we want to validate our machine learning predictions with MDC, molecular dynamics simulations and experiments. And we want to generalize this framework for other applications that require molecules with specific properties. And this diagram shows the validation procedure that we propose. So we start with our data set, and then we apply the SVM classifier, and we get some rejected examples. And the accepted ones can be used for characterization with empty simulations or experiments. And if they are still accepted, they can be later used for electrospray thrusters. Otherwise, they can be reused to refine the labels. So this is the end of part 2. Now in part 3, we are going to investigate the molecular processes that govern the plume behavior for electrospray clusters. And this part actually covers more than 50% of my PhD. However, we discussed all the results during my exam 2 years ago, so I will just go quickly over the problem statement and the methodology and results. So in the original figure that I showed for the electrospray cluster, I only showed a simplified view of the plume, but in reality, the plume is composed of different species. There's monomers, dimers, and trimers. A monomer is a singly charged molecule. A dimer is a cluster of a neutral and a monomer. And a trimer is a cluster of two neutrals and a monomer. So in the plume, we have different species with different masses and different velocities. And furthermore, these heavy molecules, dimers and trimers, can fragment to give rise to neutrals and other monomers. And there is a consistent problem in electrospray clusters called anomalous mass loss, where in experiments, there's about 60% of the emitted mass that is not captured by the instrument. And fragmentation can give a partial explanation. However, we have collisional processes that lead to the formation of new species, and it can give further explanation for the anomalous mass loss. So the goal of this work is to develop a numerical framework to investigate the outcomes of these collisions. And now this is an embodied simulation that shows the expansion of the plume. It shows monomers, dimers, and trimers. And it also shows the fragmentation that gives rise to neutrals. And neutrals are shown in black in this animation. And this is not part of my actual research, but I did it as a tutorial with Python. And it covers the main physics. So I just wanted to show it to give the overall picture of emission. Then at the end of the simulation, we can see that the neutrals are spread over a wide angle. And some of them collide with the extractor grid. And some of them collide with other molecules because they have different speeds. So we have molecule-molecule-wall collisions and molecule-wall collisions. And the goal is to use molecular dynamic simulations to study these collisions. So we use MD simulations, and we use a software called LAMPS, and we use a reactive force field called the ReactFF. And the advantage of ReactFF compared to other non-reactive force field is that it is able to capture the breaking of covalent bonds, and therefore it can simulate chemical reactions. So we use ReactFF to study intermolecular collisions and molecule-wall collisions. However, there's some disadvantages for ReactFF. First, it is ill-defined for charge systems, so we cannot track the electrical charge of the byproducts of collision. The second disadvantage is that it cannot model a real wall. So the wall here in the simulation is a potential wall. It is not a wall composed of actual atoms. And we do a statistical analysis, so we vary the angles phi y and phi z and theta y and theta z, and we vary also the impact parameter, and we also vary the impact energy. So we get about 18,000 simulations for the first case and about 9,000 simulations for the second case. And here are the results of molecule-wall collisions. So we have 5 main pathways. So at small impact energies, less than 10 electron volts, we may have recombination, where the two molecules stick together after the collision. We may have momentum exchange, where there's just a momentum exchange, but they don't stick together. And there's charge exchange, where the monomer steals the negative molecule from the neutral. And then between 10 and 30 eV, we have ionic fragmentation, where the neutral molecule splits into one positive and one negative part. And beyond 30 eV, we have covalent fragmentation, so the entire molecule breaks apart. And you get many byproducts after the collision. And now we have molecule-wall collisions. So this is just an example at 100 eV. So we start with a molecule EMIB4, and we end up with many byproducts, as you can see in the simulation. Next, we want to, we want to derive the mass spectra of the byproducts, and a mass spectrum represents the probability of occurrence as a function of the mass of the byproducts. And from the mass, we can infer the actual species. And here you have 3 mass spectra for 3 different impact energies, 10 eV, 100 eV, and 1000 eV. And we observe that at small impact energy, we have heavy molecules, so the fragmentation rate is still small. Then as the impact energy increases, we get lighter molecules, mainly CX, HY, and Z. And then at 1000 eV, the mass spectrum is dominated by the atom of hydrogen. Next, we want to validate our results experimentally. So we collaborated with the MIT. So this experimental validation was done by the SPL lab at the MIT. So they used an array of 480 extraspheral thrusters that emits in a vacuum chamber, and they used two instruments. There is a retarding potential analyzer, or PI, upstream. This one gives the energy distribution of ions. And after the collision with the plate, the byproducts are collected by this residual gas analyzer, RGI. And from the measurements of the RGI, you can infer the mass spectrum for the byproducts. And in order to be able to compare our numerical results with the experiments, we have to average all the results over the energies. So we have many simulations. Here we have the mass spectra of neutral wall collisions at different energies. So we multiply them by the energy distribution of neutrals given by the experiment, and we get one average spectrum for neutral wall collisions. And we repeat the same procedure for monomer wall collisions. So we multiply the mass spectra by the energy distribution, and we get one average spectrum. And then we average the two based on the mass contribution, and we get one single mass spectrum that we can directly compare with the experiment. And here's the main comparison between numerical and experimental results. So the experimental spectrum is represented in red, and the numerical results are represented in blue. And the y-axis is mirrored to facilitate the comparison. So in the case of simulations, we call it probability. In the case of experiments, they call it normalized current. And we have different species here, and we see a quantitative agreement between the experiments and the numerical results. However, there's still some discrepancies. So they observe H2O and OH, which is due to the presence of residuals of water in the vacuum chamber. And since we don't have any water in the simulation, so we don't expect to see these molecules. And then there's a second discrepancy. They observed the molecule HF, hydrogen fluoride, but in the simulation, we only see the atom of fluorine, F. And there's a third disagreement here. In the experiment, they observed H2, the molecule of hydrogen, but in the simulation, we only see the atom of hydrogen mainly. And we have given some explanation to justify these discrepancies in the paper and the thesis. One of them is the fact that the distance between the collisions and the RGI is about 20 centimeters. So it gives plenty of time for the molecules to recombine and form new molecules. But in the simulation, we just stop the simulation a few nanoseconds after the collision. So we don't capture the reactions that happen between the collision and the RGI. And this empty workflow led to two journal papers and some also co-author contributions in conferences and papers. And this slide was supposed to be future work for this work, but since I stopped working on this in 2023 to focus on the machine learning project and the refueling project, so this project kept evolving with other people. So after this experimental validation, we have introduced density functional theory, DFT, and DFT is able to capture the partial charges of the byproducts, which is one of the limitations of React-FF, and it is able to capture the HF molecule. So with DFT, we don't see this discrepancy anymore between HF and F. And also DFT can model a material wall of gold instead of a potential wall, as we did with the React-FF. And this work was done by Nicholas Laws. And then we did another experimental validation between MD and collision-induced dissociation, and it showed good agreement between simulations and experiments. This work was done by Abdultaki Tahsin and Stefan Baer. And then we integrated the collisional outcomes of from the MD simulations into the embodied simulations, and this work was done by Adler Smith. And so this is for the general conclusions. These are the main thesis contributions. So at the mission level, we have developed an analytical framework to optimize on-orbit refueling strategies, and we have applied it to the Smart One mission. At the propellant level, we have developed a supervised machine learning pipeline to detect and predict aeronatic liquids, and we have identified 193 new candidates. And at the plume level, we have developed an MD simulation framework to characterize the chemistry in the plume, and we have identified the reaction pathways. And all these projects have led to 4 journal papers, one at the mission level, one at the propellant level, and 2 at the plume level. Each of these journal papers have their corresponding conference paper, and in addition to some co-author contributions. And for the future, we can think of integrating these efforts into a bigger scale. So we have our liquid candidates through machine learning screening that can be synthesized and then can measure their specific impulse and thrust experimentally. Then from the MD simulations, we can inform lifetime limiting phenomena, and we can give estimations of the degradation rate as a function of the propellant type. Then using the specific impulse, the thrust, and the estimation of the lifetime, we can feed this back to the mission level optimization. And finally, we can have a multi-scale design and validation pipeline where the propellant selection, the throttle performance, and mission architecture can be optimized concurrently. And finally, I want to thank the sponsor of this work. So this work was sponsored by 1 NASA grant and 2 Air Force grants, and partially by the Africa Fund Fellowship by Cornell Graduate School. And finally, also, I would like to thank all the Atala members. It's been a great pleasure and honor for me to meet and work with all these people over the years. And I'd like to thank my advisor, Professor Elaine Petro, for welcoming me in her lab and for the advising and all the support. And I hope for potential future collaboration. And I would like to thank my committee members, Professor Tadorensky and Professor Damel, for the support and for answering all my questions. And I had questions related to my research. And yeah, thank you.
So now we'll open the floor to questions from anyone in the room.
This, I have a question for, if you go back to the ML classification, the final plot you have. Yeah, the plot of cation mass map, yeah. For the, I understand that you're using 1,800 possible molecular descriptors, and so there's a lot of things that go into this data. Do you have any idea why there's a preference either from the physical side for the cation mass being less than the anion mass?
The cation mass. Oh, actually, I haven't thought about it. But generally, the cation is larger than the anion, like Na plus to 4 minus. And yeah, so like physically speaking, if they satisfy the requirements, they're still positive. But I don't think there is like a correlation between the ratio of cations and anions. Yeah, maybe you can investigate. You can add a feature that maybe can capture the ratio of the cation mass and the anion mass.
I had a question on the refueling section when you were showing balancing between mission payload and mission time.
Yes.
Yeah, there was like a table with a couple different cases. Right?
This one?
Yeah, that's one. Okay. Does the order matter in these, like case 2 and 3? You go 9% of the way and then
No, I think the order doesn't matter because it's the sum, so you can put it as well.
Okay, great. And then what about like external? I guess I just had questions about like what would the refueling look like? We talked a little bit about that on the Starlit project, but then you talked about having extra space when you're using less propellant mass. What about along the way? Like, are there any sort of, if you have an external propellant structure that can be used also for payload if you're not using that like docking area for propellant at that time?
You mean like additionally to saving mass with front propellant, you can also save mass by maybe ejecting some parts of the spacecraft?
Yeah, I guess I'm just wondering if there is periods of the burn where you're carrying less propellant in some of these uneven ones.
This one assumes that we carry like 100% of the required propellant at each segment.
Okay.
Yeah. So the propellant that is carried like in the first segment is different from the propellant that's carried in the second segment. Like in case 2, like we have more propellant in segment 1 than in segment 2.
So do you foresee that as being like an external propellant tank, or do you just have less propellant in
I mean,
the
like just that, like the same tank
Okay.
that's propellant.
Okay.
Yeah, that the mass of the tank was not included in this study, but you can also include the mass of the tank as there's like the tankage fraction that gives the mass of the tank as a function of the mass of the propellant.
Okay.
And yeah, so we can extend this. Yeah.
Okay, very interesting.
I had a question related to still the refueling session. So did you look if like the convenience of using it also changes with the type of mission? Like if the target of the mission is like a I don't know, close solar system planet or like a deep space mission?
Yeah, I think the type of mission influences our choice in the constraints. For example, if we want to deliver like a cargo, a lot of mass,
Mhm.
in this case, we may prioritize the payload mass and we can sacrifice the mission time. And if the mission is time critical, like for science-based missions, we can prioritize the constraint on time. That's yeah. So yeah. So I think the way we define the constraints depend on the goals of the mission.
Not hearing anyone, you can think for a few again. I guess we'll just close this to the public.
Yes. Thank you.
Congratulations.
Repeat, I guess you can help us by everyone. It's not about black.
Yeah. Just be able to work on. Still have some people online, so
If not. Yeah. You can read.
Nobody ate any of their cookies
I
on your way out.
falling asleep.
You want one now?
No, I'm still right now falling asleep.
I'm just removing people like.
Yeah. Just don't report them to Zoom.
Leave me here, I guess is the other.
Not gonna get somebody coffee.
Oh,
I mean, you won't be able to give it with me because I have a meeting right before this, and I'm like, I'm not gonna make it.
I noticed they updated the mountain coffee to lot below.
Yeah, because Cornell is divested from Starbucks. Finally.
Yeah.
So forever.
So we think about that.
Yeah, after they closed down Starbucks
Right.
University, finally.
Good.
I can't say the quality of coffee has actually gone up.
I haven't tried it, but I was just like,
From a political perspective, I am not displeased.
yeah. The other day, I feel like somebody was like, oh, something about coffee from mountains. I was like, I don't drink coffee from mountains.
Okay, how are we doing?